Hello and welcome to this SCION Instruments webinar. My name is James Hogan and I'm the Applications Lead Scientist here at SCION. Today's webinar is the Import and Export of Chemicals EU-UK REACH Substance Identity Requirements. In this webinar we will focus on what REACH is and what it covers, what it's responsible for, and we will also focus on gas chromatography and how it can be utilised for a vast array of substances to help meet these regulatory requirements. So now to kick off the webinar properly, we will start with the topic of what is REACH. So REACH stands for the Registration, Evaluation, Authorization and Restriction of Chemicals. It is the main EU law to protect human health and the environment from the risks that can be posed by chemicals. The European Chemicals Agency, or ECHA, is the regulatory body responsible for the implementation of the REACH legislation, among others. REACH covers any chemical without its own specific regulation. And the trigger for REACH is any chemical that is imported or manufactured greater than 1 tonne per annum. REACH applies to almost any chemical substance that are either produced or imported into the UK or the EU. This may be a substance on its own, a substance existing in a mixture, or a substance within an article. So just to break that down into a little bit more detail, registration is a requirement to collect, collate and submit data to the European Chemicals Agency, or ECHA, on the properties of all substance with the current exception of polymers and non-isolated intermediates. This applies to any substance manufactured or imported into the UK or the EU in quantities above 1 tonne per year. Certain substances of high concern, such as carcinogenic, mutagenic and reproductive toxic substances, will also have to be authorised. So evaluation. This provides a means for the authorities to require registrants and in very limited cases downstream users to provide further information. So authorization. This authorization requires attempts to ensure that risks from the use of such substances that require it are either adequately controlled or justified by socio-economic grounds, having taken into account the available information on alternative substances or profiles. So this covers substances of very high concern, or SVHCs. So REACH has substance identity requirements, and ECHA defines this as substance identification is a process by which the identity of the substance is established. So accurate identification of a substance is a prerequisite to most REACH, CLP and biocide processes. So CLP is the Classification, Labelling and Packaging Regulation. This is another European Union law that requires companies to classify, label and package chemical substances and mixtures in a uniform way. So substance identity requirements will, the parameters for these will be based on the type of substance. So we have two types. So we have what's known as well-defined substances. So these are defined as monoconstituent substances, where the chemical composition is one main constituent that is present at greater or equal to 80%. And there is a requirement here that any impurity found greater than or equal to 1% will also be required to be identified. We then have multi-constituent substances, which are known as unknown or variable composition, complex reaction products or biological materials, or UVCB for short. So these are defined as substances with chemical composition, a mixture of main constituents, each between either equal to or greater than 10% and less than 80%. There's a requirement here that any compound present in the substance equal to or greater than 10% requires identification. So something else to be aware of is what's known as a substance identity profile, or a SIP. So this isn't a requirement for all substances, but what you might find is that some lead registrants will provide a SIP. And what it is a percent range of the expected components that you would expect to find within the substance. What it also may define is specific impurities that must be screened for. So this is more common for UVCB, the more complex mixtures, and can help guide the testing requirements. So without it, you're sort of on your own, really. So it's something that's worth looking for. So I have a quick example here. So a product that's known as C9 to C14 aliphatic, 2 to 25% aromatics, very catchy. And this substance, the lead registrant had provided a SIP. So they had defined expected percentages for different compound groups, and this would therefore help determine the testing. And there's also a requirement for benzene to be present less than a certain amount for each product type. So this is just a quick slide that I've chucked in just to sort of highlight the real importance of REACH and of this testing. So this is an article taken from the ECHA website. It's referring to hazardous chemicals found in cosmetic products. So in 2024, 4,500 cosmetic products were tested, and 285 of these were found to contain chemicals, the use of which is banned in these products. So roughly 6.3% of the products tested were found to have hazardous chemicals that are banned. So it really does highlight the importance of REACH testing and of this regulation. So if you're all still awake and still with me, we'll move on from regulations and start to discuss the role that gas chromatography can play in this testing for this regulation. So let's take a look at the uses of gas chromatography, or GC, for REACH testing. So with the GC, we're able to analyse volatile and semi-volatile substances, and because of this, we therefore will cover a wide range of substances that are covered under REACH. So for example, organic mixtures, gaseous mixtures, volatile components, natural oils can be analysed with gas chromatography, to name a few. We're able to cope with different sample types, so we can analyse gases, liquids, solids, although there may be some sample prep considerations need to be made. So this may just be dissolving in a solvent, or maybe some kind of an extraction. We are also able to analyze complex mixtures, so we have the ability to separate and analyze mixtures containing many components, which makes this a really powerful tool. So I just want to quickly focus on one of the reasons why gas chromatography is such an effective technique, and that is the range of detectors that we have available to us. So I'm just going to quickly run through some of the detectors we have at SCION Instruments and that are commonly used in the world of gas chromatography. So we have flame ionization detector, or FID. This is useful for the analysis of organic compounds. We have nitrogen phosphorus detector, or NPD. As you may guess, this is a discriminative detector for compounds containing nitrogen and phosphorus. We have the electron capture detector, or ECD. So this will detect compounds capable of undergoing electron capture reactions, such as halogens and select nitrogen and oxygen compounds. We have the thermal conductivity detector, or TCD. This is incredibly useful for permanent gases. It's also a non-destructive detector, so it can be combined with another detector, and this makes it incredibly versatile. We have pulse flame photometric detector, or PFPD. This can be used in two modes. So we have phosphorus and sulfur mode, and then nitrogen mode for these specific compounds containing these components. We then have a mass spectrometer, specifically the single quad mass spectrometer that's really useful for REACH testing. So this can be used as a mass scanning device, and it's very, very useful for identifying unknowns, which is obviously a requirement for REACH testing. I don't have too much time to go into these detectors in great detail today, but if you scan this QR code here, you will find our online guide, which goes into great detail for each detector. So I'm just going to run through a couple of example substances that could be tested under REACH regulations. So I'm going to start with a monoconstituent substance. So this is a substance that is present at greater than or equal to 80%. So in this example, we analysed a bottle of eugenol that had been imported to the UK under REACH regulations with the bottle claimed a purity of 95%. So we analysed it on a GCFID. You can see the chromatogram in the report here. So we found the purity to be 96.9% by percent area. We found one unknown impurity greater than 1% at 2.4% there. We just have an enhanced chromatogram there, so you can see how we've been able to separate out all the different components there. So we can see the eugenol peak, the main peak there, and then the impurity peak as well as the other smaller impurities that are present within the sample. We were then able to use GCMS to confirm the identity of the main constituent, so eugenol. We were also able to identify the impurity that was found to be present greater than 1%. So this was found to be 3,4-isopropylphenol 2-methylpropionaldehyde, so a really catchy name, or a CAS number of 103.95.7, which is a little easier to remember. So this is just a really quick example to show how a really simple system, so it was just GCFID with a split-splitless injector, could be used for the purity determination, and then we were able to use our 8700 SQ for analyte confirmation of both the main constituent and also the impurity that was required to be identified under REACH. So I've got a couple of more complex examples here, so UVCB samples. So The best way to do this for such complex mixtures, so we can see an overlay here. So the red chromatogram there is a mixed standard, a mixed hydrocarbon standard. So we have C8 to C40, and then we're able to profile this sample based on the carbon number. So this was an oil that we were able to profile using this technique. And then we have another example here with a really complex sample. So we're able to use the gas chromatograph to separate out all the components, but because it's such a complex mixture and there's such a mixture of components within there, then we can use this technique of profiling using the mixed hydrocarbon standard. So again, this was quite a simple configuration. So it was just a GC FID with splitless, and then we were able to again confirm some of the identities of the main constituents present using GCMS as well. So we may find that some compounds aren't particularly well suited to gas chromatography, but there are some techniques that we should consider which will allow us to analyse these sorts of components. So for example, the injection technique can be something that's really important to consider. So we may want to use something like cool on column or programmable variable temperature injection. And this can be really useful for compounds that are heat sensitive. So you may have a complex mixture where some of the components, you may have very high boiling components, you may have very low boiling components. So what we can do is ramp the temperature of the injector, which will slowly volatilize each component, and it may help prevent some that are more heat sensitive from degrading, and will then allow us to continue to ramp the temperature to the higher boiling components to allow them to volatilize and move on to the column. On our website in the Knowledge Centre, we have extensive guides, just like the detector guides, on all of our injectors. So if you'd like to know more, please take a look on there. Another technique that we may want to use is something called derivatization. So this is where we can react compounds, so compounds that aren't suitable for analysis on GC, that may break down or degrade for some reason, usually due to heat again. We can react these to form more suitable components. So this may be compounds with poor detection or heat sensitive components. We do also have a guide on derivatization that can be found in our Knowledge Centre, so please do take a look. Something else we can use is what's known as a retention gap or a guard column. So this will basically protect your analytical column and will therefore help reduce instrument downtime. Really useful for really dirty samples and is especially advantageous when we're doing cool on column or splitless injections, as it really helps focus the liquid onto the column with these large volume injections. So I just want to talk about some further considerations of reach testing, mainly where GC can't work for you and you will have to consider different analytical techniques. So there is a requirement for additional testing. So we have the requirement for testing of purity and for analyte confirmation using MS. We also require additional spectral data. So for example, FTIR, UV and NMR. And just to highlight, here at the TechComp group, which is the group that SCION is part of, we do have our sister company that provides, so for example, Edinburgh Instruments provides IR5 FTIR spectrometer and their DS5 UV vis spectrometer. So within the group, we do have a lot of the instrumentation required for reach testing. As discussed, we may find that there are compounds that are unsuitable for GC, and one alternative is LC for purity determination. So here at SCION we have the LC6000, we have diode array detector available, UV, refractive index and fluorescence detector as well. There also may be a need for other characteristic tests. This will determine on the sample, on the substance that you're requiring to analyze. So it may be things like loss on drying or moisture content and ash testing. So for example, again, here at the TechComp group, we have TechComp lab products or the Precisa Prep Ash thermogravimetric analyzer that could be used for ash testing, for example. We also have a moisture analyzer as well. So we've got you pretty well covered for quite a few of the requirements for reach testing. So now I'd just like to quickly sum up this webinar. So hopefully I've given a good overview of what reach testing is and also the role that gas chromatography can play in this testing. So I've tried to emphasize the importance of reach testing. One thing I'd just like to say here is that the reach regulation allows easily accessible information on chemicals for end users. It's also led to a reduction in the need for animal testing. So what it's allowed is sharing of information on these different substances to different importers. So they're able to limit the number of tests required. Different tests that are required on animals can just be done once, and then they can be shared between different registrants. We also therefore now have determined the chemical properties of these substances that have been either manufactured or imported, and there's also authorization for hazardous chemicals and moves to reduce the use of these and to seek alternatives as well, which is a great effort. So gas chromatography, so the main use for gas chromatography and reach testing is for the purity determination, so both for monoconstituent and for UVCB substances, and then obviously we can use MS to confirm the identity of the relevant constituents, so anything greater than 1% in a monoconstituent substance and anything greater than 10% in a UVCB substance. So there are other considerations for reach testing. So there is a requirement for other tests. So for example, for purity, GC may not be suitable. So we may be able to use LC, for example. There's also a requirement for further spectral data, so UV, FTIR, NMR, and there may well be a requirement for things such as moisture content and ash content as well. So all things to be aware of in the extensive requirement for substance identification. We have a QR code here. This will take you directly to our application note on reach testing, so please take a look. So thank you very much for your time today, and please do take a look at our Knowledge Centre and our guides online. Thanks very much.